All right, welcome everyone to the Explainer Hackathon. I'm your lead dev for today, and we are going straight after a very specific, incredibly high-tariff mainframe. We're talking about formulating differential equations from rates of change, specifically for the Cambridge AS and A-Level Mathematics 9709 syllabus. Now, if you actually want to clear the examiner firewall here, you cannot just treat this like any ordinary math problem, you have to treat it like an algorithm. Today, we're going to break down this notoriously complex, multi-part problem using strict, code-like syntax so you can absolutely maximize your output. Let's get into it. So you might be wondering, why are we targeting this specific mainframe right now? Well, it's because formulating differential equations from rates of change accounts for roughly 15% of your total marks in Paper 2. Think about that. That is a massive data packet. It makes this topic a super high-stakes target for any serious exam coder. If you can master the syntax here, you are literally securing a huge percentage of your final compilation score right out of the gate. Okay, here is our system roadmap for today's hackathon. First up, we'll outline the target mainframe. Then, we'll move into debugging the matrix. Third, we'll be compiling the patch. After that, we'll jump into the interactive beta testing arena. And finally, we'll wrap up with code deployment. Section 1. The target mainframe. Let's start by identifying the core problems that students almost always run into when trying to breach this specific module. I want you to really think about this for a second. Why do so many students find the distinction between key terminologies so incredibly hard? We've looked at the principal examiner reports, which, let's be real, is basically the ultimate server error log for past exams, and those logs show that candidates consistently confuse key terminology. This confusion right here is a primary source of point loss across the board. It's essentially the equivalent of a fatal syntax error that just completely crashes your entire program before it even runs. To put this into perspective, we generally see two distinct types of candidates in the system. Let's introduce our virtual test subjects. First up, Dev Alex. Now, Alex has phenomenal raw data inputs. They know the math, the underlying numbers are solid, but they cause major memory leaks because their analysis is completely unsystematic. They just jump straight to the final answer. Then, on the other hand, we have Dev Sam. Sam totally understands the logical loops, but completely fails the syntax precision rules. We're talking missing definitions, improper notation, the works. The takeaway here is that raw mathematical skill just isn't enough if you lack systematic analysis or if you ignore those strict presentation conventions. That brings us to Section 2, debugging the command matrix. Now we need to actually map out the theoretical architecture required to get past that examiner firewall. Okay, let's dive into this because this is absolutely crucial. You have to understand the method mark strategy. In the Cambridge system, marks are awarded for the process itself, not just spitting out the final output. Think of the examiner as an automated compiler. They genuinely want to award you points, but they can only do that if you explicitly show them the right architecture. You have to prove the correct procedural framework, and you do that by using clear notation and appropriate formats. If you just print the final answer with no working, the compiler rejects your code entirely. No exceptions. So how exactly does this build into the core principles of the exam? Well, the test prompt is never just asking for a number. It's specifically targeting three distinct cognitive domains. First, knowledge and understanding. Simply put, do you know the underlying formulas? Second, application. Can you successfully apply those formulas to the specific rate of change given in the prompt? And third, analysis. Can you use real evidence-based reasoning to extract relationships from the provided texts and tables? Your final code literally has to satisfy all three of these domains to get full credit. And to successfully execute that method mark strategy, you've got to follow some incredibly strict conventions. These are the exact syntax rules that DevSam usually fails at. We're talking proper headings, absolutely correct terminology, appropriate formats, and crystal clear annotation. These aren't just nice to haves, they are completely mandatory. This is the exact formatting required to get your solution to compile successfully with the Cambridge examiner. All right, I'm going to briefly halt the compile screen right here for a rapid mid-explainer patch. If you're a focused learner looking to truly master these systems, you need to optimize your feed right now. Hit subscribe on @the_exams and turn on all your system notifications. We push out these updates weekly to help you totally crack these past papers. Okay, patch complete. Let's head back to the terminal and push this high-scoring code. Section 3, compiling the patch. Let's outline the exact core methodology you're going to need when your logic inevitably runs into an error mid-argument. For this, we deploy what we call the deconstruct, solve, evaluate framework. This is our absolute optimal syntax to fix any logic error you might encounter. Step 1 is deconstruct. You identify the given information and meticulously extract the relevant data from the text and tables. Step 2 is solve. You select your analytical framework, break the problem into logical steps, and execute it using that clear notation we talked about. Finally, step 3 is evaluate. You check your final output for reasonableness and make justified evidence-based conclusions. Seriously, if you run this specific loop on every single differential equation problem, you bypass those common memory leaks entirely.
Moving on to Section 4, the beta testing arena. It's time to initiate some immersive reader audits and see how well you can spot the bugs. But before we actually test your skills, let's pull some raw data directly from the principal examiner reports. According to the examiners themselves, these are the top 3 crash-causing bugs. Number 1, using the wrong approach for the context. Number 2, forgotten format and presentation. And number 3, answers that lack specific context. Let's create a quick memory hack acronym for this, WFC. Wrong approach, format forgotten, context missing. Memorize that. You have to guard your code against the WFC bugs at all times.
Okay, test 1 in the beta testing arena is a trend extraction. The system logs clearly show that an examiner alert is instantly triggered the moment candidates confuse key terminology. The patch for this is surprisingly simple, but it is critical. Always define your terms before using them in your extended responses. If you're going to use a variable for volume or a variable for time, you have to define it explicitly right at the start. If you skip this step, it's an instant syntax error, and you lose the mark. Next up is Test 2, a code review focused on contextual specificity. So where do most students completely fail here? The major bug is that they leave their final answer as a raw, abstract mathematical equation. Remember, formulation of a differential equation from a rate of change usually models a real-world scenario, something like water draining from a tank or population growth over time. Your mathematical answers must explicitly match that given real-world context. If your final equation lacks that context, it immediately gets flagged by the system and you drop those vital marks. Finally, Section 5, Code Deployment. It's time to review our optimized text string and see how you can elevate your performance from standard to elite. Let's do a quick comparison between standard coding and elite architecture. A standard candidate approaches a differential equation by entirely isolating the problem. They just do the math in a vacuum. But a top-scoring candidate, they use an elite cheat sheet architecture by deliberately integrating cross-topic connections. The examiner reports explicitly highlight that candidates who reference these broader connections achieve significantly higher marks. Elite candidates show exactly how the differential equation connects to integration, to kinematics, or to graphical analysis. They see the whole system, not just one line of code. I really want to read this direct quote from the source data because honestly, it is the ultimate algorithm to ace the specific 15% module. Quote, top-scoring candidates demonstrate evaluative thinking by questioning assumptions, considering different perspectives, and justifying decisions with evidence. End quote. What this actually means is that when you set up your rate of change equation, you are systematically proving exactly why it works. You're evaluating your causal relationships, and you're communicating all of it with absolutely perfect terminology. And with that, your system is now fully optimized for the Cambridge 9709 Differential Equations module. To make sure your firmware stays completely updated for all future exam modules, make sure you subscribe to @AceTheExams right now. Click that Dell icon and drop a comment below with your specific subject and level. That way, we can custom build the next masterclass update specifically for you. I'm going to leave you with one final provocative thought to process in your own terminal. When you open your next past paper and you face down a massive high-tariff rate of change question, what is the very first assumption you will question when applying the deconstruct, solve, evaluate methodology? Think about it, run the code, and I will see you in the next explainer.